Hello and welcome back to Physical Geology. I am Robert Lopez, and today I want to continue on with Chapter 2, but start looking at Earth's magnetic field and this idea of paleomagnetism. So one of the things we should look at is Earth's magnetic field is really a force field, and it causes magnetic material like lodestone. Lodestone is a mineral magnetite to and the force field, it's going to do work. It's going to cause these magnetic minerals to point in the direction of magnetic north, right? So move and align to magnetic north, right? And so you can think of our field as like a dipole. And a dipole is like a bar magnet. It has two poles, a positive end and a negative end. And usually what we have is that there's always a line that seeks the positive end. So lines of force on the bar magnet kind of loop around. I think I showed this in the other diagram or another video, but they'll loop around and make these magnetic lines of force. So this force field around the bar magnet. Remember, planet Earth is going to be a little bit different, but it's kind of the same concept, right? And so we'll do that down over here. So magnetic lines of force leave the so on Earth, right? So this is, what's that here? This is for Earth here, because it's a little bit different than the bar magnet, but it's the same concept, right? So if we think about the bar magnet, we're going to put it in here, right? So let's put the bar magnet in Earth here. And so note that we're going to have the positive end here and the negative end here, right? So lines of force will leave magnetic south and re-enter at magnetic north, right? So they're going to make this looping field that goes around the planet, right? Looping field that leaves the southern hemisphere and re-enters the Earth in the northern hemisphere. And it happens at all latitudes here, right? At all latitudes, leaving and re-entering here. So if we had some arrows, it's going out this way and then re-entering up in here, right? We'll put the arrows going down in here. And so note that at the equator, or near the equator here, the lines of force are going to be parallel. They're going to be parallel to Earth's surface, right? So the lines of force are going to be parallel to Earth's surface down over here. So here I'm showing the lines of force leaving magnetic south and re-entering. So up here at magnetic north. So there's a couple of points I want to add here. So there's this GN up here. And so GN and G south, what that means is that means for geographic. And so it refers to either geographic north or geographic south. So that's the axis upon which Earth spins. So basically, this is the North Pole or the South Pole, right? And those don't move. What we'll find is the magnetic field or the magnetic north and magnetic south do fluctuate, right? Because they're caused by, you'll see they're going to be caused by currents that in the outer core, the liquid outer core of Earth, right? So just note that there's a difference between the geographic poles, so this is GN and GS, and the magnetic poles, right? Magnetic south and magnetic north. So, and so let's look at this word magnetic declination, right? So currently today it's about 11 degrees. And that's the angle between magnetic north and true north or geographic north, right? So it's a deviation, the angle between magnetic north and geographic north, right? And that one's changing. It's changing, and I'll show you a slide on that in a moment. And then this magnetic inclination, this one here is the angle the magnetic lines of force make with respect to Earth's surface, right? So angle, and we'll call it magnetic lines of force. Make with Earth's surface. And so you'll see that this varies in different parts, right? So over here at the poles, this is a high angle, close to 90 degrees, right? Close to 90 degrees. We know that the equator, this is 0 degrees, right? because the lines of force are parallel here, right? They're parallel to Earth's surface. And then up here again at high latitudes, they're going to be something, and again another high angle. So you'll see that inclination is going to be really important, because the rocks, because when the lava erupts, the magma is going to have these minerals. In fact, let's look at the next slide. I think I have an example of that. Yeah, so here I have a question. How are rocks magnetized, right? And so we'll have to look at basalt. Remember, basalt is important for three reasons. I sort of hinted on this in the last video, but the first one is it's abundant, right? It covers the ocean floor. Remember, the ocean floor makes almost 71% of the planet. So by far, it's the most abundant rock, volcanic rock on Earth's surface. Secondly, it primarily erupts at mid-oceanic ridges, right? And then, as we'll see later on, using this paleomagnetism, we'll find that it's a key piece of evidence for seafloor spreading, right? And so what is this word paleomagnetism? Remember, paleo means ancient, right? So we're looking at some ancient magnetism. And it's really an ancient magnetism found in rocks. And I actually have the definition up here. So remnant magnetization found in rocks. So the rocks, sort of, it's a permanent record. The rocks, once they acquire the magnetization, they have a permanent record of Earth's magnetic field in the geologic past, right? Right. So that's where the paleo comes from. Now, if we look down here, remember, basalt is a mafic rock, and it contains tiny magnetite minerals. Remember, those are the lodestone minerals that are affected by Earth's magnetic field. They're gonna, in fact, really, they act as tiny compass needles. Tiny compass needles. And when the lava erupts, in fact, we'll look at the steps here. When the lava erupts, the minerals, these little red lines represent the magnetite minerals. And note that they're all random, right? So they're all random. But then note that these lines here, B here refers to a field. So this is the magnetic force field. So this is the Earth's magnetic force field coming down here. And so the minerals start to sense that, and they're going to start rotating and move into position, right? So magnetite free to move in 3 dimensions, right? So it can move in the left-right direction or the up and down direction, right? So it's free to move in 3 directions. And so what happens, the little magnetite minerals align themselves in the same orientation as Earth's magnetic field. And remember, if we could draw a horizontal line through here, right? Remember the angle right here. That angle is the inclination. That's an inclination. And so if these lavas erupted near the equator, the inclination should be close to 0, right? Just like on our slide over here, the inclination should be parallel to Earth's surface. But since they're at an angle that's going back into the Earth, right, where the lines of force re-enter the Earth, are up here in the northern hemisphere. So they're probably mid-latitude northern hemisphere. So maybe around 45 degrees, 50 degrees north, right? Because that's the angle. You can measure this. That'd be about 45 degrees right there. So paleomagnetism can also give hints as to where the rock formed in terms of latitude. You know, what latitude it formed in. So it's a proxy to position on Earth's surface. And then remember, plate tectonics, seafloor spreading is going to move this rock from its original position, and it's going to end up someplace else, right? All right, so we have the magnetite reorienting themselves based on, you know, like tiny compass needles, right? And then lavas cool below this Curie point, and that Curie point is 580 degrees centigrade. So so that's a temperature at which these little magnetic minerals, the magnetite, get locked in, and we end up making a permanent record. So now we have the paleomagnetism. Now this rock, through plate tectonics, is going to be moving, and it's going to remember its original position of formation, right? Even though it's moved to a different position on Earth, right? So that's the phenomenon of Earth's magnetic field and paleomagnetism, right?